Hello, and welcome to today's lesson on chemical measurement. In this lesson, we will firstly gain an overview of some of the key principles in chemical measurement, including uncertainty, significant figures, and taking a mean. Then we will move on to understand how to apply these principles to enhance the accuracy and reliability of our chemical data. So far, we've explored essential quantitative chemistry concepts: the mole, which we explored as a unit for expressing a specific quantity of a substance or particles; percentage by mass, which we calculate using relative atomic mass and relative formula mass; atom economy, which tells us the efficiency of a chemical reaction; concentration, which uses mass and volume; and gas calculations, which explore temperature and pressure in order to determine the number of molecules. These principles have given us a strong foundation in understanding and calculating chemical quantities and reactions. Building on this foundation, today's lesson will advance our chemical understanding by introducing the principles of measurement. Mastering uncertainty, significant figures, and calculating the mean will enable us to analyze and interpret chemical data more precisely. This deeper insight into measurement aids in enhancing experimental accuracy, which is crucial for reliable scientific outcomes. Let's dive into the core principles of chemical measurement: uncertainty, significant figures, and calculating the mean. Every measurement we make in chemistry carries some degree of uncertainty. This uncertainty can arise from various sources. One common source of uncertainty is limitations in the measurement tools we use, such as thermometers or balance. Many tools have an uncertainty value written on them that helps gauge their accuracy. For example, if a pipette has an uncertainty of plus or minus 0.06 milliliters, if you measure a volume of 25 milliliters using it, the volume could be anywhere between 25.06 milliliters and 24.94 milliliters. If an instrument does not have an uncertainty value written, then we estimate its uncertainty plus or minus half the smallest scale division. For example, if a thermometer has a mark at every 2 degrees Celsius, then it has an uncertainty of plus or minus 1 degree Celsius. If you measure the temperature to be 10 degrees Celsius plus or minus 1 degree Celsius, for example, this means the actual temperature can be anywhere between 9 degrees Celsius and 11 degrees Celsius. This range indicates the possible true values the temperature might have. We can reduce this type of uncertainty by using a tool of higher resolution. For example, a thermometer with 1 degree divisions instead of 2 degrees. Such a thermometer would have an uncertainty of plus or minus 0.5 degrees, meaning if you measure the temperature to be 10 degrees Celsius, you can be sure it is actually between 9.5 degrees Celsius and 10.5 degrees Celsius. This is a smaller range than using the thermometer with a lower resolution, which increases your confidence in the results. For a digital instrument, we can calculate the uncertainty using a similar method. The uncertainty is half the smallest increment. For example, if a mass balance can measure to 0.1 kilograms, then its uncertainty is plus or minus 0.05 kilograms. This means that given a reading of 1.0 kilograms, the actual mass can be anywhere between 0.95 and 1.05 kilograms. Similar to analog devices, this uncertainty can be improved by using an instrument of higher resolution. For example, a scale that measures to 0.01 kilograms. Being aware of sources of uncertainty is crucial for accurately interpreting and communicating our experimental results. Due to these uncertainties and potential errors, it's common practice in chemistry to take multiple measurements and then calculate the mean value. By doing this, we can minimize the impact of random errors and obtain a more accurate representation of the true value. To find the mean, you simply sum up all your measurements and divide by the number of measurements you took. For example, if you measured the length of an object 3 times and got the values 1.1 centimeters, 1.0 centimeters, and 1.2 centimeters, the mean would be calculated as follows: 1.1 plus 1.0 plus 1.2 equals sign 3. 3/3 equals sign 1.1. Here, the mean length is 1.1 centimeters. We can estimate the uncertainty of a set of repeat measurements as plus half the range. Remember that the range equals sign largest reading, smallest reading. In this case, the range is 1.2 minus 1.0 equals sign 0, 2. Therefore, the uncertainty is 0.2/2 equals sign 0.1 centimeters. We can present the measurement as 1.1 plus 0, 1 centimeter. Suppose we have an experiment where we measure the time taken for a reaction at different temperatures. You and 2 other friends conduct the experiment and you collate the results. Suppose your results were as follows. We can calculate the mean for each of the temperatures as shown. We can calculate the uncertainty for each measurement as we did before by calculating half the range. This is a lot of information. We can represent this graphically on a temperature versus reaction time graph. We start by plotting the mean readings normally. Then we can draw a curve of best fit. However, how do we represent the uncertainty? When we take repeat readings in experiments, we often represent the uncertainty in our measurements using vertical bars on a graph. These are called error bars. They help us visualize how precise our data is and make it easier to compare different sets of results. Take the 40-50 reading, for example. We have found that to have an uncertainty of plus or minus 2. Graphically, we will draw an error bar that extends 2 units upwards and 2 units downwards. We can do the same for the other data points. This gives us an easy visual tool to better evaluate our data. For example, we can see that the error bar for the 50-29 point is particularly long, indicating a large uncertainty. This tells us to do further investigation and take more repeats at that temperature in order to be more confident of the results. Note that what we have covered here regarding error bars is slightly above what you need to know for your GCSE exams. However, it's extremely helpful for further understanding and contextualizing the idea of uncertainties. Now we'll look at significant figures. Significant figures are an important part of reporting scientific measurements. They help convey how precise a measurement is and ensure that we don't overstate the accuracy of our results. In chemistry, we often use 2 or 3 significant figures. For our previous example, if we round to 2 significant figures, the mean becomes 1.3 centimeters. And if we round to 3 significant figures, it becomes 1.33 centimeters. It's important to note that when performing further calculations with these rounded numbers, the number of significant figures should be consistently applied to maintain the integrity of the data. Understanding significant figures is elaborated on in the skills section of chemistry. Understanding uncertainty, the importance of taking multiple measurements, and the correct use of significant figures is fundamental to mastering chemical measurement. Let's dive into some GCSE level questions to apply our understanding. Question 1. A student measures the mass of a substance 3 times and records the following masses: 4.5 grams, 4.7 grams, and 4.6 grams. Calculate the mean mass and estimate the uncertainty. To calculate the mean, we add up all the measurements and divide by the number of measurements. We add up all our values, which gives 13.8. Then we divide by the number of values, which is 3. This gives 4.6 grams as the mean. To estimate the uncertainty, we find the range, then half it. To find the range, we take the smallest value away from the largest value. So 4.7 minus 4.5 equals 0.2. Then we divide this by 2 to find our uncertainty. So the mass is 4.6 grams plus or minus 0.1 grams. Question 2. Using a balance which measures to the nearest 0.01 grams, a student measures a mass as 5.30 grams. What is the range of possible values for the mass? The mass balance in question measures to the nearest 0.01 grams. Hence, it has an uncertainty of plus or minus 0.005 grams. The uncertainty indicates the range within which the true value lies. The mass is 5.30 grams, plus or minus 0.005 grams. The true mass could be anywhere between 5.295 and 5.305. By practicing these types of questions, you'll become more proficient in applying the principles of uncertainty, significant figures, and calculating the mean to chemical measurements. These skills are essential for ensuring the accuracy and reliability of your experimental data. In today's lesson, we delved into the principles of chemical measurement, mainly focusing on uncertainty, including the various ways to calculate it depending on context. We explored how uncertainty arises in measurements and how it can impact the results of experiments. We also learned methods to minimize and report uncertainty to provide a more transparent depiction of our data's reliability, including taking repeat measurements and calculating a mean. We also discovered how to represent uncertainty graphically using error bars. Overall, these principles are crucial for interpreting and analyzing chemical data. They help us ensure that our measurements are precise and reliable, which is fundamental for achieving accurate scientific outcomes. By mastering these concepts, we can enhance the quality of our experimental work and make more informed conclusions in our studies of chemistry.